Hi, this is video 1 on chapter 20 and 21 combined. In this video, we're looking at expected value of a sum. We are essentially interested in looking at finite sum of random variables, right? So until now, we've been looking at the expectation of a given random variable, but now we are interested in the sum of that. And that is known as the linearity of expectations. So for example, as this theorem states here, if x of I, where I can take values from 1 to some n, are random variables on S, and if a and b are real numbers, then both these together make up something that's called the linearity of expectation, right? So as you can see, the expectation of all these random variables x1 plus x2 and so on up to x of n is equal to the expectation of each of those taken as individuals, right? Similarly, the expectation of any expression of this form where x is my random variable and a and b are some constants is actually equal to a multiplied by the expectation of x plus b, which is a constant. Now together we can state this in a more concise format, which is this, that states that the expectation of the sum of all the expectations of a random variable xi for all multiplied by some constant a of I, such that this is also changing with each I, right, is nothing but the sum of the expectation of all the x of i's multiplied by that constant, right? So this is the more generalized form of the linearity of expectations theorem, but we can definitely break it down into the top two steps. Okay, so with this, let's look at the proof of this theorem. And the way we can state that in words is that the expected value of a sum is a sum of expected values, right? As we saw in the equation itself. So let us assume that x1, x2, and so on are some random variables. So x1, x2, x3, and so on up to, let's say, x of k or n, whatever you want to call it, right? These are my random variables, and I can express these as a1 and then z is a linear combination of all these random variables, right? So a1 x1 plus a2 x2, and these a1s and a2s, they are some constants, right? Like, for example, numbers. And x of k is a linear combination of x of I. Then the expected value of z is given by, so I'll just substitute this the way I defined it, right? And is a linear combination of for all xi's. So E of z, simply by substituting, is going to be a1 x1 plus a2 x2 and so on up to ak of xk. Right? Now, we, according to the theorem that we stated in the previous previous slide, this must be equal to a1 of expectation of x1 plus a2 expectation of x2 and so on expectation of xk. Sorry, this has to be e. Okay, so one way of proving this, that this is equal to this, and this is just a statement until now, and now we have to prove it, is to think about the definition of the expectation, right? So this is my statement of this expected value of a sum is the sum of the expected value. Now for the proof, right? By definition of expectation, E of z is given by, and this goes back to our previous lecture, so you can go and refer to those slides. But by definition, for all x's that belong to S, which is my sample space, because z is my random variable, so I'm just using that for all values of the random variable for all x's times the probability for all x's, right? So we know that by definition. By definition, this is known to us. Okay, so if we want to expand this, right, we also know that this is what z is, right? So this is also known to us, right, that z is a linear combination of all these x's. So basically, this points to the fact that x belongs to S, and z of x can in turn be written as a1 x1 on x plus a2 x2 on x, and so on up to ak, and then x k of x, and this entire thing is multiplied by the probability of x, right, for each x essentially. And then we can take out the constants out of the summation sign, right? So we can have for all x's in S x1 over x times p of x, right? Again plus a2, and then a similar expression for x2, and so on up to ak, and then summation x belonging to S x of kx times p of x, right? And by the definition of expectation, this here is the expectation of x1, right? And this is going to be the expectation of x2, and this is going to be the expectation for x of k, right? So we know that by definition, right? So I don't have space to write it, but I'll just like write down that by definition we can say that this e of z is going to be a1 times e of x1, a2 of x2, and ak of xk. So we have proved that e of z is equal to this, right? Or in turn, this is equal to this, either one of them, right? So this was the definition and a proof of linearity of expectation. Let's look at some of the applications of linearity of expectation in the next video.